My dog's barking.
Yeah,
so I feel like I might be a little bit older than some of the other people attending the class. I'm 33, but I have a background. Well, I graduated as a history major.
Sorry,
but
I'm having a little trouble. Is anyone else having trouble understanding this? Yeah, we're adjusting the speakers. I think potentially.
Well,
Okay, well, we find out if we'll be able to hear people. Course logistics, you can still turn in assignment 1. So do that. Okay, well, maybe we should get started. Yeah. Okay, yes. Sorry, introductions didn't work out great. Oh, they can now. Do we want to try that again, or should it be?
Can you hear me?
Okay. I think maybe in the interest of time, we'll bump that to next time now.
Right.
But if you have questions, feel free to speak up throughout. We're going to be covering quite a lot. There's three pretty hefty topics up here. We're going to be talking about syntax, semantics, and embeddings today. So, we'll go through a lot of material pretty quickly. So that's going to necessarily mean glossing over some things. So, the goal isn't for you to get a deep technical understanding of everything, but at least gain some familiarity with things. But, ask questions as we go, and I'll try and answer them. Also, like Anthony said in his lecture, there's, math at various points in the presentation, but if that's helpful for you, then that's excellent. But if it's not familiar to you, feel free to, glaze over in the eyes and just listen to the explanations of things. And that should also be a cohesive story. And similarly with, certain diagrams and things, for the most part, if they're not helpful, it's not super important that you understand the details of them. But we'll go into as much detail as we can. So the driving questions of this lecture are the following. How do you determine the meaning of an expression? So how are we getting meaning from language? And how can we represent meaning so that a computer can reason about it? So more explicitly, what we're going to try and do is start to think about meaning and language in a critical way. We're going to introduce you to some formalisms and intuitions so that you have some tools to start thinking about linguistics and meaning. And then we're going to look at a couple of ways that you might encode linguistic information for natural language processing tasks. And at the very end, hopefully we'll have some time to think about how to evaluate the quality of those representations. Okay, but we'll start with the first question of determining meaning from language. And we're going to start in particular with a philosopher of language who we'll come back to later, and logician and linguist, Frege, who has the principle of compositionality, where the meaning of a complex expression is determined by the meaning of its structure and the meaning of its constituents. So very roughly, that's going to be, the structure is going to be a discussion of syntax, and the meaning of its constituents is going to be our discussion of semantics. And putting these things together is going to be the meaning of a sentence or an utterance. So we'll start with syntax. And, we've already in previous lectures seen how, structure of words and things and how we combine parts is very important in determining meaning. And this should be a familiar concept. In math, we have an order of operations where violating that order really changes the meaning of the expression. And similarly in grammar, let's eat, comma, grandma is calling grandma to dinner, and let's eat grandma is having grandma for dinner. So, comma save lives. Structure is important. And when we're talking about structure, we're putting parts together. So what are those parts? They're called syntactic categories. These are the syntactic parts that we're thinking about building up the structure of. And so these are things that you're probably familiar with, parts of speech, so we have nouns and verbs, and those combine to form noun phrases and verb phrases and sentences. And they build together in a kind of structured hierarchy to put together a full sentence. So what we have on the screen right now is something called a syntax tree. We're not going to talk too deeply about how to build these, but they are a representation both of the syntactic parts of the sentences, but also how they're combined, which does affect the meaning. But we'll talk about that in less formal terms than the tree. So when we think about sentence structure, maybe a more familiar way to think about it that you've been taught your whole life is the idea of grammar, right? That's rules about how we write sentences and how we use language. And indeed, many of these rules are important for communication. So for instance, rules about word ordering. They may mean different things, but hopefully you can understand the meaning of a sentence, Bob likes Sally or Sally likes Bob. But like Sally Bob, that doesn't make sense. There's no way to really internally parse that. So rules about ordering are important, and sometimes violating them gives you gibberish. But you probably also heard other rules in class, like, don't use passive voice, or less for mass nouns, fewer for count nouns, don't end sentences with prepositions. And these are rules that tend to be how people think language ought to be used or should be used. But we often find that violating these kinds of rules, you can still convey meaning, right? So I could say, that's not something I want to put up with. And that's a reasonable thing to say. You understood what I meant, but with is a preposition, and I've ended my sentence with a preposition. And in fact, sometimes following these rules sounds really awkward to a native speaker. So for instance, there's the famous Winston Churchill quote in Congress when somebody told him not to end sentences with prepositions. He said, "This is the type of art and pedantry up with which I will not put." So, which is pretty awkward, but does not end with a preposition. Okay, so those rules about how language ought to be used is the idea of a prescriptive grammar, right? But we're more interested in how language is actually used and the ways in which you can put it together, and still sound meaningful to native speakers. And so that's more of the project of building a descriptive grammar, which describes how language is used. And we're going to think about that in reference to something called a mental grammar, which is basically the idea that you have some internal kind of black box that you're using in your brain that you're using to interpret language. So a mental grammar is the system that all speakers of the language have in their minds, which allow them to understand each other. And we consider a sentence to be grammatical in this definition if it follows the rules of the mental grammar of native speakers, for instance, right? So if it if it makes sense as a sentence. And if it does, then we consider it to be a well-formed sentence. But this doesn't necessarily mean that the sentence is like plausible or feels particularly meaningful. So there's this famous example from Chomsky, who is a famous linguist, that colorless green ideas sleep furiously. So this is a sentence and it is grammatical, but I don't know what it means. And it doesn't really conjure any kind of mental image that I can reason about. I think we probably don't have time to read this, but as a fun also nod to an important principle that we'll be talking about for most of this lecture, which is the importance of context and word meaning. In the 90s, Stanford had a competition to come up with a context in which colorless green ideas might sleep furiously, and hopefully we'll send out slides or something and you can read this, it's fun. But yeah, so summarizing just our little discussion of syntax so far, syntax is the structure of sentences and utterances. When we think about syntactic categories and their mode of combination in syntax, we've seen that sentence structure plays an important role in determining the meaning, the sentence or utterance. And there are different types of syntactic rules, but ultimately we're going to be most concerned with the ones that are derived from the way people actually use language. Okay, and here's the first instance of, or another instance of diagrams that you shouldn't worry about understanding too deeply. But these are building syntax trees or identifying the part of speech of different words or sets of words in a sentence are very common natural language processing tasks that are related to understanding syntax. And these are sometimes used, these tasks are often sort of useful for an end goal in and of itself, like there's the task of named entity recognition. So, looking for keywords in a sentence. And these are also often used to validate how successful an embedding is, if it can be used to do these tasks. And if that sentence didn't make much sense to you, that's fine, because we're going to talk about embeddings shortly. Right, okay, but before that, we're going to talk about semantics. So this is the part that has to do with the meaning, like the constituent parts of our sentence. And a theme in this is going to be, a theme in this is going to be that words in different contexts can have different meanings. So in this cartoon, Turtle is talking to Snail, and Turtle says, "This is a river. It's water that's going places." So what's a lake? That's water with nowhere to be. And a pond? The most laid back of all water. Very funny. This is poorly drawn lines. Great comic strip. I recommend it. Okay, but to be a little bit more formal about it, we're going to go back to Frege, our philosopher of language, our logician. Then this is kind of where linguistics and logic meet up, and you get the concept of sense and reference of a word, right? Okay, so the sense is the mode of the presentation of a word, or you can think of it as the mental representation you have of a thing or concept as it's presented to you in language, whereas a referent is a physical thing in the world. So here we have Will talking to Nico, and Will is talking about that cup, which incites Nico to have a mental representation. He has a sense. He has an understanding of the sense with which Will is using this word cup. But Will is, of course, referring to a real thing in the world, which is the cup on the counter, and that is the referent of the word cup here. In more formal settings, words that you talk about the referent as the set of objects in the world that match the definition of a sense. And so, for adjectives, like things that are blue, that's helpful, because then it's the referent would be the set of all things that are currently blue in the world. Or for like intransitive verbs, the set of all things that are currently walking would be the referent of walking, or that kind of thing. And so to understand a little bit about why it's important to separate these things, and also why it's important to our discussion now for building up notions of word relatedness, here's a couple of example sentences to think about. So the first one is, MJ does not know that Peter Parker is Spider-Man. Okay, what's weird about this sentence is Peter Parker is Spider-Man, right? They're the same, and in the world where they exist, they have where he actually exists, like they have the same referent, same guy. But how can then it be true of Spider-Man that MJ knows that he's a superhero, but it's not true of Peter Parker that MJ knows that he's a superhero if they're the same thing? Okay, so that's where sense and reference comes in. So I can reason separately about the sense of a word and the reference of a word. And that's sort of a very central concept in like philosophy of language and in lexical semantics, which is the kind of semantics we're currently really talking about. But it's also helpful for building up word relationships that you might be familiar with, right? So, and defining them in a principled way. So we have the sentence, I think you should put the couch here, or I think you should put the sofa here. And they kind of mean the same thing, right? Couch and sofa not only probably have the same referent in this case, but have really similar senses. So a synonym is two words that have the same sense, or very nearly. I took out money from the bank after donating blood to the blood bank. Okay, so this is two usage usages of the word bank, they have different senses, right? But and completely different reference. One is a financial institution and one is storing blood, but but the senses actually have a relationship to one another, right? They're both storage institutions, and like the words and the senses are related, and that's the relationship of polysemy between words. You also have things like hyponymy and hypernymy, which is the notion of like a subcategory of. So a poodle is a hyponym of dog, and dog is a hyponym or a hypernym of poodle. Okay, and so why are we talking about this? Because one of the things that we're going to try and capture when we get to our discussion of embeddings is we're going to try and capture a notion of word relatedness. So that's going to be something we're going to build to. And also, this helps us couch the way we're thinking about words in a kind of semantic web of related words, right? And the structure of this web contains meaning. So if I were to put another word, if I were to put corgi up here and attach it to dog so that it was in the same kind of relationship and connections to dog that poodle had, then that's pretty easy to derive that it's also a type of dog, you know? So we want to start getting comfortable with the idea that similar relationships to words in a web or in space, like that can have meaning in and of itself, and that can tell you something about words. Okay. This is very close to building to our topic of embeddings, but we're going to take a quick pause to add another topic to our already crowded lecture, because it's important to remember that it exists. Because if the meaning of a sentence really was just the meaning of its parts and it's the way that they were combined, then our job in natural language processing would be pretty easy, right? Like all the information we need is there. But that's not necessarily the case, right? We use a lot of outside context, things that are outside of documents or sentences to enrich our understanding of things. So there's this Levinson quote, an utterance is not, as it were, a veridical model or snapshot of the scene it describes. Rather, an utterance is just as sketchy as the Rembrandt drawing, right? But you can still, this is just some scribbles, but you can still look at it and use your own kind of cognitive enrichment to understand that this is, you know, probably Jesus and disciples, and there's an archway, and, you know, all of this really rich imagery. Similarly, you might take a tweet like this: Cats is undeniably a film, brimming with a score, cinematography, and performances. It's a motion picture made by a team of filmmakers that can irrefutably be described as existent. Truly one of the films 2019 has to offer. Okay, so we can probably understand that this person did not like the movie Cats, but nowhere in this tweet is there anything that's like explicitly negative or that contains that information. So we're enriching it with our own personal like understanding of context, and that's the role of pragmatics, right? So context is important, and we should remember that. Okay, good. So before we talk about embeddings, what have we done so far? We've talked about syntax, we've talked about the structure of language, we've talked about semantics, we've talked about senses and references. We've used those concepts to build up a notion of word relatedness and put those together in a kind of web of semantic relationships where connections and relationships in the context of that web kind of contain some meaning or help us figure out meaning in and of itself. And then we pointed out that we should remember about pragmatics, reminding us that the words in the structure of a sentence don't tell the whole story. We enrich meaning of a sentence with an understanding of broader contexts. Okay, I'm gonna pause quickly if anybody wants to ask any questions. Cool.
In your Parker Spider-Man example,
yeah,
were there different references or different senses?
Different senses. So they both refer to the same thing in the world, and this is also assuming we're in the world where Peter Parker and MJ exist. Because you can also have, I think I maybe didn't talk about it, but there's like the sentence "I love unicorns" was on there, and unicorns is something that has a very clear sense. Like if I say that, we can all think about it and understand what it means, but they don't exist in our world. So in our world, they have an empty set as the referent, but like philosophers love reasoning about possible worlds and modal logic and all that kind of stuff. So in the world where Peter Parker exists, they both have the same referent, which is the person to whom the name Spider-Man and Peter Parker both belong, but they're different senses of the word. Because yeah, they sort of are different modes of presenting a pointer to the same referent, but they carry different information, and we can reason logically about them separately. Cool. Any other questions?
Just a note in general, it might be best to repeat the question if the question is asked, just because we're not.
Oh, right. That.
But I think we got that.
Yes, thanks. Okay, cool. Okay, so now we're going to talk about embeddings. And this is a really important concept in machine learning, and we're just going to start to build up intuitions about it. And in Friday's lecture, you're going to hear a lot more about sort of modern tools for making what we're going to call word embeddings. And but we're gonna take a first pass at thinking about these things. Okay, so what is an embedding? It's a thing. It's a vector. It's a representation of some input object. So whether that's an image or a sentence or a word, we often do things where we take that image and we, in some way, whether it's with a neural network or some other mechanism, we turn that into a number or a list of numbers, which is a vector, so that a computer can reason about it. And in our case, we're going to be talking about how to take words and map those to vectors. Okay, and in case we've forgotten, vector, it's just an ordered list of numbers. The length of that list is the dimensionality of the vector. The dimensionality of the vector can also be thought of as the dimensionality of the space in which the vector is mapped or is plotted, right? So if I have like XY coordinates, then that's a vector of length 2, and I would plot it on a plane, a 2D space. And if it's length 3, then I would plot it in a three-dimensional space. And maybe you can't imagine it after that, but that's going to keep scaling, and we're going to talk about dimensionality. Yeah, and we can represent a vector either with its set of coordinates as a list of numbers, or sometimes we'll plot them on some kind of axes. Okay, but I've been talking about vectors. Why would we bother with vectors? Well, machines are really good at matrix vector manipulation. Yeah, so, and GPUs are pretty optimized for doing big matrix multiplication operations and these sorts of things. So that's helpful. We can also store a lot of information efficiently if we're clever about it. Yeah, and this is the standard way to represent word meaning in natural language processing, and we use these representations for lots of different tasks. In natural language processing, what we tend to do is, like, when we take words as just, I think Phoebe talked about sort of parsing words into different like subparts or phrases and different lexemes. But however you're parsing your sentence, say just like into words, the intermediate step that I've sort of glossed over here, and we're gonna talk a lot more about this notion of vector representation. So if that doesn't make sense yet, that's also fine. But basically, you're going to take a word, you're going to assign it an index in a vocabulary. So if I have, for instance, the words dog, bat, and tree, then I might assign, and that's like all the words that I know, I might assign them each a number. And then from there, so that's the first step of encoding a word for a machine to think about. But then, so that's the little hand wavy thing that we didn't talk about in the function image. But then from there, you're going to map that number to the vector, and so those are two steps that machines are good at. Okay, so that was a logistical note. It's not a particularly high concept. Okay, cool. So we want to take words and we want to represent them as vectors so that machines can do stuff with them, because machines are good at operating with vectors. Our first pass attempt, like a very simple model of how to do this, is with one-hot encodings. So a one-hot encoding is a vector of all zeros and 1, 1, where that 1 is indicating which element of like our set of options this vector is referring to. So in this case, with our vocabulary of dog, bat, tree, the one-hot encoding, the set of coordinates 1, 0, 0, we're just going to assign to dog. The next one will assign to bat. The next one will assign to tree. And you can either think about those represented as vectors as lists, or plotted on a space. In this case, these vectors are all mutually orthogonal, so they're each going to be of length 1 along one of the axes. Here we only have 3 words, so we only have 3 dimensions, so I can plot them all for you. But you tend to have, many, many thousands of words in your vocabulary. So if you're plotting them in this way, you're going to have a really, really high dimensional structure that you're going to be thinking about. But yeah, so here's a first pass where we've taken words, we've assigned them in a one-to-one way to vectors, and we can think about them as being plotted in a space, and the vector space is just the space in which these things are plotted. So it's this set, this world of 3 axes. Okay, this is great. We did it. We have vectors, so we can do computation, and that's great. So that's a pro, and it was also pretty simple, pretty easy idea to understand. But can we do better than this in how we're going to represent words? Yes, because where are these lacking? So they're very inefficient, right? They're very sparse, which means they're mostly zeros. And so they're, informationally or space-wise, they're very inefficient. Well, I guess you can press them, but they're also very inefficient in terms of how much informational content they contain, right? Because all it does is indicate which word in a vocabulary we're pointing to. It doesn't have any of these semantic properties that we talked about of containing important relationships between words or any of that kind of thing. So since all of the words are mutual, all of one-hot encodings are orthogonal to each other at right angles to each other, if we think about this down here is basically a dot product. If that's not familiar to you, you can just think of it as it's a notion of like how similar two vectors are, like how much they point in the same direction. And for one-hot encodings, the encoding for motel and hotel have 0 overlap in the same way that hotel and cat have 0 overlap. But it feels like there should be some relationship between the encoding that we have for motel and hotel, where we can see that they are semantically close in meaning, and that this is as opposed to the relationship between hotel and cat, which don't really have anything to do with each other. Okay, so I said that context would be very important, and it is. And so starting to think about context is going to be how we're going to take our next pass of trying to build up word embeddings. So in natural language processing, a very successful idea is the idea of distributional semantics, which is the idea that a word's meaning is given by the context in which it appears, so the distribution of the words around it. And you can define context in lots of different ways. In the 2 examples we're going to see next, we'll see context as the set. So if the word W appears in some document, then its context we could consider to be the set of all other words that appear in that document. Or we might look a little bit more locally and just say, it's the surrounding words. It's the 4 words that appear before it and the 4 words that appear after it, or some other notion of like much more local context. But it's a very literal notion as opposed to a pragmatic notion of context. Yeah, so then there's the famous quote to that effect: "You shall know a word by the company it keeps." So context is important. Okay, cool. So one way that people will build up word vectors beyond one-hot encodings is by building various co-occurrence matrices. So, in a Word document co-occurrence matrix, what you're looking at is so one axis is going to be all of the documents you care about, and here it's 4 plays from Shakespeare, and then you'll have a set of words. You might have the set of words of all of the words that appear in all of the documents, but for simplicity, I just have 4 words here. And then you get in this case, you get +1 for every time you occur in that play. So battle appears once in As You Like It, good appears 114 times, fool 36 times, and so on, in each of these plays. And then we can think about the rows of this matrix, this table, as giving a vector representation of the words. Incidentally, you can also take the columns and use those as representations of the documents to reason about, which people sometimes do. But we're going to be talking about word embeddings. Yeah, and you can already see that we're starting to get something that's a little bit better than one-hot, right? So fool and wit are both words that have to do with humor, and battle has to do with what Julius Caesar and Henry V were up to, and drama. And fool and wit have kind of sort of line up, right? They're big in the same areas and small in the same areas, and in a kind of inverse way to how battle is. Okay, so we're starting to see that there's some relationship encoded in these vectors. Okay, but now we're going to think about the other notion of context we described, which is the sliding window idea of a word-word co-occurrence matrix. So the last one was when words occurred in a document, and now this is going to be when we're going to keep track of, for cherry, this is going to be the number of times each of these other words along the top axis appeared in a fixed size context window. Okay, so here's some examples. If we're looking at just the 4 words, if our context window is size 4, then we're just looking at the 4 words before and the 4 words after when we're building up our word-word co-occurrence matrix in this sliding window context fashion. And similarly, we're going to take the rows of this co-occurrence matrix, and we're going to call that a vector representation of our word. Okay. And again, you can start to see that you're getting something for your work. You're getting something better than what you had with one-hot encodings. So looking at it graphically, we can pick sort of two words, computer and data, and plot how often in some big corpus of documents those words appeared in the context of digital, information, strawberry, and cherry. And we see that they occur a lot in the context of digital and information, whereas you can't even see strawberry and cherry on the plot because they're so small. Not only that, but digital and information kind of point in the same direction. So they have a similar relationship between computer. They're similarly related to both computer and data, and are thus like quite related to one another. Whereas cherry would be pointing more this way. So so the angle between the vectors is also tells us that they're very close, and we'll talk about that a little bit more. Yeah, and so the next thing we're going to do is take a quick pause actually to think about how we might look at a plot like this and start to evaluate the word vectors, since we're now building up a bunch of different ways that you might represent a word as a vector. So are there any questions here? Okay. Is there anything in the chat? Okay, cool. Yeah.
Most existing models that use this rare words that like aren't usually used don't exist in the model. Like if there's a word that doesn't appear naturally in text but dictionary,
Yeah.
that wouldn't exist in models like this, right?
Yeah, and so often what you'll do in that case. What? Oh, right. Sorry. So the question was, in your full dictionary of words, you have a lot of words that are not going to occur very often. So if you're just looking at a document set, or co-occurrence of words, like there's a lot of characters or words that you feel like you might never see. Usually what you'll do is you'll have a special token, which will look like open in brackets like UNK for like an unknown token. And you can just sort of put all of the infrequent words in a bucket together and all under the umbrella of this unknown token. You also sometimes, if they don't come up, you just don't include them in your matrix altogether. Although the notion of the fact that new words can appear that are outside of our corpus is a problem that we have with these kinds of matrices, right? Because not only do we have this issue that they don't exist in or we have this issue where they don't exist in our matrix. So if we want to add a word to a representation, we have to change the whole dimensions of our matrix, and we have to, especially if it's word-word co-occurrence, and then we have to get all new word vectors, and that's like a bad time.
So for models like these,
Yeah.
I know that like we know digital and information they mean something similar because of like the angle.
Yeah.
So, but do we also read into like the magnitude of the vector?
Yeah.
So with rare words, they would have like smaller magnitude, so the model can embrace in that sense too.
Yeah, so it depends on what you're trying to get out of it. And the next couple of slides are going to talk a little bit about how to understand, like how to compare vectors. Very often, actually, you don't want to pay attention to magnitude. You care more about the angle. So there'll be a slide on this coming up, but so we can talk about it then. But it tells you something different about it. It tells you that information is a more common word, and that is a piece of information that for certain tasks you might want to utilize. But if you're just interested in isolating the semantic meaning of all of the different words, then you're more interested in where they point to in space than in how long they are. So you'll often see word vectors plotted along particular axes that are hand chosen, like up here. Sometimes you'll see them with their vectors. Sometimes you'll see them just kind of plotted in a cloud, and they won't have their arrows and the axes. But this is still, putting them at points in a two-dimensional space, and you can understand these as, being rays coming out of the origin. Oftentimes you have more than 2 dimensions that you want to and you don't have a principled way where you just want to look at computer and information or something. Like you don't want to cherry pick these axes, but you still want a way to visualize your word vectors. And so you'll do what's called a 2D projection, where you essentially take the matrix of like all of the word vectors, and you do various tricks to come up with 2 important axes to plot that are somehow capturing a lot of meaning. That was a very hand-wavy thing to say, because explaining how these work is I don't think we really have time for. PCA works on singular value decomposition, if that's helpful to anyone, and TSNE is more clustering. But these are 2 different ways that people will sometimes represent high-dimensional data in 2 dimensions, where it still captures sort of something about the relationships between how the vectors would be in the actual high-dimensional space. But keep in mind, so this is the same data with 2 different projections, and you can see that they look quite different, and you can see much stronger trends in one than the other. So just, also be aware that the 2D representation is missing a lot of things, and how you choose to go about making it does, sort of affect what conclusions you might draw from it. And so those are some ways to sort of visually evaluate word vectors. But we probably want some computational tools, especially since these things tend to exist in such high dimensional spaces where you can't really visualize them as well as you'd want to. And we want to be able to let the computer reason about it. So this is sort of exactly your question, right? So if I were to take what is a very simple notion of comparing two vectors, and I were to take the dot product between vectors in this graph or in this plot, the dot product takes the amount that sort of, say, this lighter red vector projects onto this darker red vector. So the dot product would be big because they're both long. But it's sort of a notion of vector similarity that magnitude matters for. But since we said that but what we want is that things end up near each other in space. That's what we really care about with our vectors. We want things that have similar meanings to point somewhere close to each other. But the dot product between these two vectors, oh, I'm not pointing to anything, between the two shorter vectors is going to be smaller, despite the fact that they point to almost the same spot. So we're going to want to correct for that. And so while people sometimes still use dot products, and there's a list of other metrics people will sometimes use. So if you're interested later, you can look some of these up. Probably the most common, though, is cosine similarity, which is basically taking the cosine of the angle between two vectors as a notion of their similarity. This makes sense because it's essentially like a length normalized version of the dot product. So it's exactly the point that you were asking about. So that was a great question. Yeah, so we go back to this. Okay, here the axes are different. We have computer and pi, so that cherry shows up a little bit. And we can see that the cosine, or the angle between cherry and information and digital is really big, but the angle between digital and information is really, really small. And so that's like emphasizing that they're really similar in meaning. Okay, cool. So what have we done so far? Just taking stock again for a moment. We introduced this idea of embeddings, of mapping words to vectors, and those vectors exist in a vector space where like collectively they're all plotted. Relative location in that space is going to, or ideally, if we've been successful in creating good word vectors, is going to be semantically meaningful. We looked at a couple of different ways that you might go about building word vectors. We talked about one-hot encodings, word document co-occurrence, word-word co-occurrence. The V's and D's off to the side are like the dimensions you would probably see these vectors in, where V is the size of your vocabulary and D would be a number of documents you had in your corpus, but it's not especially important. Before we move on, there's also, and if this doesn't make a lot of sense, this is not a very important bullet to understand, but one other way that people will get word embeddings is they'll take these co-occurrence matrices, so the stacked on top of each other, all of the word vectors, that gives you a matrix. They'll use tools to factorize that matrix, and then so you use SVD, and then you take the principal components and you get this, and then you can kind of like chop them shorter. If that was helpful to anyone who is listening, great. If not, really don't worry about it. But that is something that people do. Okay, good. So, and again, to your other question, these vectors that we've talked about have problems. So every time we add a new word, the dimensions of everything we've been doing change, and so we have to often start over. The matrices themselves tend to be very sparse. Most words don't occur with one another, so we're not like densely packing in information. And they tend to be really high dimensional, and that ends up being computationally costly in all sorts of ways. And so that's something we want to avoid. And if you are doing this matrix factorization, you have to do it on the whole matrix, and it's also computationally expensive. Okay, so Before we talk about how we might do better, are there any questions now? Yeah. Yeah. So that's a great question, because that's sort of the crux of the idea that these kinds of vectors are presenting, is that being used often together is somehow the same as meaning, or at least gives you a good idea of meaning. And so we're using the idea that two words often show up near each other as a proxy for defining their meaning. But that might feel very unsatisfying. And if you are unsatisfied, get ready for Friday. It's gonna be great. But yeah, no, that's exactly the crux of what we're doing, is we're relating those things. Yeah, so the next thing, and like a set of ways of embedding words that was really successful were these iterative-based methods. The one we're going to look at in most detail is word2vec. Yeah, so it's a supervised learning method for getting word vectors based on you had a lecture on machine learning, but we're going to start this is just uses linear regression. I won't talk too much about how that works, because that's a little bit outside the scope of what we have time to talk about, but I'm happy to talk about it. And any of the details that we gloss over in this, like after the lecture or in like the office hours, or if you're around, find me at any point. But basically, you're doing machine learning on the task of predicting context from a center word. And that's going to be the kind of the proxy task we're using to tell the model that we want it to learn meaning. And in this case, it's going to be basically that we have our we have our matrix that is stacked on top of each other, all of the vectors that are our word vectors. And those are also what we're going to call the parameters of our machine learning model. And through gradient descent optimization, you're going to update those model parameters until we like them enough, and then we'll call them our word vectors. Yeah. And this is called an iterative method because rather than, that's as opposed to matrix factorization methods where you have to look at the whole matrix and do a very computationally costly thing all at once, whereas here you're kind of looking locally in text and you're making one prediction about local context over and over and over again. Yeah, okay, let's see. So we have about 10 minutes left, which is not really enough time to go through the math of this and also talk about the upshots. So what I'm probably going to do is give you just an outline of the algorithm that they use for word2vec, a little bit of a description of other sort of similar methods that people do, and some kind of like closing thoughts. So, but if you're interested in the math, both there's going to be more descriptions of it in the slides that you can go back to. I think we can send people slides. And there's also a lot of really good internet resources that take you through how word2vec works with like code or just in writing, and it's very well documented. Okay, but basically what this approach is going to do is we're going to start with a large corpus of text, so a lot of like a big body collection of text, and we're going to again fix our vocabulary. So then say all of the words that appear anywhere in this corpus, that's our vocabulary, and anything that's outside of that is going to be like our unknown token. And we'll randomly initialize a vector for it. So we have this big old matrix of randomly initialized numbers that we're assigning, one vector of, so one row of to each of the words in our vocabulary. And actually, we're we're going to have two representations of each of the word, because we're going to learn a different representation for the word as it appears as a like center word and as it appears as a context word. That's sort of a note on implementation as opposed to like being a real important part of the crux of the idea though, so don't get too hung up on that. And then basically what we're going to do is if T is some position in the text, so it's like T is 5 means we're looking at the 5th word in our big body of text. We're going to say the word that appears at T, that's W sub T, we're going to treat that as the center word, so C. And we're going to say that C is surrounded by context words O. So we'll fix our window size. We'll fix like how big the context on how many words on either side of our center word we care about. And we'll put all of the words that appear in that fixed sized window, and we'll call them O. Those are the outside words. They're the context of the center word C. And then for each C, we're going to calculate the probability, like what the model thinks the probability of that, the words in O being the context of C is. So given that we have C as our center word, what is the conditional probability that O are the outside words? And our model's going to use dot products and things, like a notion of a vector similarity of what it currently has, to come up with that probability and make a prediction. And then we're going to, based on that prediction, adjust, or we're going to have a loss function, and then we're going to adjust using linear regression and try and get better at making the probability of the real context words high. And you can include other things of negative sampling and try and make sure that it's low if it's not in the context. But it's basically, trying to increase the probability, or make it so that the word vectors are such that using them, we can use a notion of similarity behind the scenes which is an equation that I will point to maximize the likelihood of the true context words that surround a center word. And that's going to be our training objective for our model. This is very centered on the idea of conditional probability, which is Bayes' law, which is something that's worth taking time to understand properly. But we don't have that time currently. But this is built on an idea of conditional probability, right? So what this means on the left side of equal signs is, in a world where B is true, how probable is A, right? So in a world where if event B is that I have a cold, then it's going to be pretty probable that I have a fever if A is having a fever. But given that I don't have a cold, it's less probable that I have a fever, for instance. So conditioning on one event changes the probability of the other event. If that wasn't particularly meaningful for you, like this comes up a lot, it might be worth thinking about, but also we can glaze over and we can move on. And so here's where I'm going to start skipping through some slides pretty quickly in the interest of time. So this is sort of showing how the algorithm looks at the conditional probability of the surrounding words given a center word. These are slides that sort of explain how the objective function of the machine learning model works. It involves the idea of a softmax function, which is something that you'll see a lot in machine learning to get a set of probabilities out of your model. But the thing to understand is that the objective function of the model is built on a notion of similarity that has to do with taking the dot products between the current model's representation of the center word and the model's representation of different possible context words. And that's going to be how we're going to get our probability out. Okay, so that was pretty hand-wavy and pretty fast. Again, there's a lot of online sources that do that slower and better, and the slides have a decent amount of annotation in them if you want to try and go through it yourself. But that idea is going to be put together into an objective function, which is probably something you heard about in our lecture on machine learning, and you'll see then that. But yeah. So again, since we're wrapping up, we're just going to look at the kinds of things that you get out of this. So once you've done your word to vec procedure, you have a set of word vectors that when you do some lower dimensional projection, you see things that you like. You see words that have some kind of semantic relationships to each other ending up in similar areas. You know, you see water and sea next to each other, and climate, wind and ice and stuff are near each other, and that's great. You also see all sorts of really cool like interrelationships between the vectors that like work in a compositional way. So one very talked about example is that when you do word to vec, you get this vector for queen and king, and this vector for man and woman, such that if you subtract the vector man from king and add to it the vector for woman, you get a vector that points pretty close to where queen actually is, right? And this kind of thing shows up in all sorts of relationships. So if you take, you know, France minus Paris plus United States, you'll get something that points really close to Washington, D.C. And this was like all the rage, everyone, and a lot of early word vector evaluation was done on whether or not they had this like semantic compositional property. People worry about it a little less now because it's shown to be not the most important for success on like the actual NLP tasks we care about, like whether it's, you know, part of speech tagging or document searching or question answering or whatever else. But it is a cool property that you see and that people are focused on. Yeah, there's some variations, but the same idea of the word to vec, where word to vec was a skipgram model where we're predicting context given a center word. You can also predict a center word given context as an objective for your function. Glove was an approach that looked at global context rather than just local context, and that was of this like sliding window, and that was another successful thing, but it's still this kind of like iterative machine learning approach. And you can use all of these things for your cool downstream tasks. Since we're wrapping up, just one note of warning is to be careful of bias in these word vectors because they are trained on text that, you know, people wrote. So just like you have this relationship where the difference between man and woman is sort of the difference between king and queen, you also find things like the difference between man and woman is the same as computer programmer and homemaker. And you get similar things where like adding, you know, where doctor and nurse become very gendered, and like there have been studies that showed like embeddings of different names, like which were used in like hiring algorithms, had similar properties where like names of particular groups of people mapped close to words like, you know, like late and unreliable, and you know, so beware of the bias your vectors are learning is a note, and be excited for next week when you learn the modern way that we get most of our word embeddings, which is with transformers, which are like MVP of natural language processing. So that's gonna be great, and that's an hour. So quickly, we'll talk about the answer to the questions from last week. So, or do you want to go over the answers, or is they can look at them later, and there's some other answers which are or questions for this week which are discussion-y, which I guess you can also look at if you have to go because it is now the hour. But yeah, are there any questions? Cool. All right. What? Like QAnon?
Yeah, they all like their symbology. So like, oh, these numbers.
Oh yeah, they would love this. Yeah, yeah.
Do they do,
People
like this vector stuff on the like,
do they actually? Yeah.
I don't know. I don't think there's anybody that smart in the.
But people do love to find a pattern in numbers. This is true.